Okay, so I'm going to put these two together. I know I'm going to have this big division bar in h. I know the common denominator here is this. And then the top is going to be the x squared, right? Minus the x plus h quantity squared. And it doesn't seem like you're going to be able to do much with that. But in fact, if we multiply this out now, the x plus h squared, if I do x plus h times x plus h, what's the first term I'm going to get? If I do x plus h times x plus h? X squared. And aren't I going to subtract that?
Yes.
And that x squared is going to cancel with that one, right? So do you see that without actually having to do it? Do you see the x squareds canceling?
Yes.
Okay. The more you can see ahead of you, right? The brighter your headlights are in the math world, the easier it is to progress. If every step is you just copying somebody else because someone showed it to you one time, that is a little bit more difficult. All right, so I'm going to do x squared minus, expand this,
X squared plus x.
plus xh.
No, yeah, 2xh.
So I did that in my head. I wouldn't expect that necessarily you would be able to do that in your head, but I would expect that you could do x plus h times x plus h, and then that, and put it together and get this. Yes? And I also put in parentheses because I'm going to subtract the whole thing. Very, very important, right? If I'm going to subtract this thing squared, I'm going to subtract every single term that comes out of it. Any questions? I'm going to go ahead and put the h over 1 now, because I'm getting close to that point where I'm going to flip that up. We good? What is this new numerator going to be after you pass this negative through and cancel stuff out? What do we have?
X squared minus x squared.
So they're gone. X squared minus x squared is gone.
Yeah.
And then,
Negative 2x8.
then,
No, negative.
Oh, I'm sorry, I wrote it down wrong.
And then negative
Right.
x squared
negative h squared
over x squared.
over my common. And then all of this over h over 1. Which now, is it all right if I flip it now and bring it up? So I would really be multiplying this times what? 1 over h. You got this?
I'm confused on how you got top.
Okay, so if you pass this through, this negative through, your next line would be x squared minus 2xh minus h squared. Right? Distributing your negative through here. These x squareds cancel.
Oh, okay, that makes sense.
Yeah?
All right, gotcha.
That's what I was saying when you try and, like, why did I expand that out? Like, nowhere else in the problem did I actually expand it out. I always kept it together. The reason I did it here is because I realized that if I expanded it out, that x squared would actually cancel with this one. Anything else you see?
Can you do like on the top
Can you-
h parentheses?
Yes. Okay. So John is suggesting that we factor an h out of this.
Yes.
Very good. Why, John? Just for fun? Because what?
Just wouldn't be as fun without doing that.
That's right. I mean, why go this far and not have that extra bit of fun? What's going to happen here?
H's are going to cancel.
You see the h's? Are gone. And now what you're left with is your answer. There's nothing else we can do with this. So our final result is negative 2x minus h over x squared plus x plus, times x plus h quantity squared.
And just to clarify, in your second to final step,
Yes.
you just took the h and the negative 2xh and the h from the x squared and factored it out.
That's right. I looked at these as being two terms that have a GCF. The GCF is h. I pull an h out. This is what would be left. I did that because I saw this, well, because it was there, we factored it, and we're just like factoring machines now. And so we just cancel it. Yes?
Do you have to factor out that h, or can you just cancel it
In
out?
calculus, that is going to be your ultimate goal. You will start the problem, and your desire will be to get that h. That h that was on the bottom in calculus will always be there, and your goal will be to make it go away. So the factoring of the h at the end here is going to be your final step come calculus. And we're going to practice more of this in this class. It's going to be connected to what's called the difference quotient. All right, and I'll introduce it later. And you'll have problems that'll have difference quotient in it, like from here on to the end of class, just for the repetition of practice, and to see what kind of algebra is in here. All right, that was fun.
So calculus, nothing but fancy algebra?
Calculus 1 is a lot of algebra. Yeah, Cal 2 assumes you've got all that down now, and Cal 2 is a different animal. Totally different animal.
So Cal 2 basically assumes that everything from calculus and college algebra is just like embedded in you now.
You know, the problem with Cal 2, here's what makes Cal 2, in my opinion, so difficult. Because if you ask anyone who's taken all the calculus sequence, almost 100% of them will say that Cal 2 is the hardest of the three.
Even harder than Cal 3.
Yes. And the reason is because there's so much information in Cal 2 that has to be covered. And you get to a point where, like in this class, the algebra you're doing right now, there's a process. There's kind of like, okay, if you see this, do this. If you see that, do that. And then you start to pick up some instinct here, right? Like what to do. But it's very mechanical. Very mechanical what you're doing here. Cal 2 is the first place where there's intuition that you can't teach. It's very hard to describe. Because I'll get up there and I'll show the class, like here's what we're trying to do. Okay, this is what we're attempting to do. Here's a new problem. What do y'all think? And I'll ask the class, how do you want to go about this? And someone will be like, well, why don't we do that? And I'm like, how did you see that? I don't know, I just saw it. That's right. I mean, you can't teach someone how to see something.
So it's almost an intuition. Right?
It's a lot of intuition. But it depends a lot on how good you were in Cal 1. So the only way I can make it easy to understand here is Cal 1 is learning to walk, okay? Cal 2 is learning to walk backwards with your eyes closed, okay? So that's it. If you can't walk forward, you're not walking backwards.
Let alone with your eyes.
With your eyes closed, right. And the better you are at walking, the better you're going to be able to go backwards. I don't know if that is good enough, but how many of you need Cal 2? Okay. I'm not saying be afraid of it, but you want to go into Cal 2 as a strong Cal 1 student. You need like A, B, you need to come out of Cal 1 with an A or a B to have hope in Cal 2.
What's an example of the Cal 2, bro?
What's that?
Like, what's an example of the Cal 2, bro? I just want to see
Just
one.
try it.
Like the simplest, but kind of hard to see.
Day what?
Simple but tedious.
This would be good for me to watch.
Okay, I'll just show you one that's geometric. I mean, we can't work it. There's no way we can work this problem. All right? But I can show you what the problem is.
If I get it right, you give me 20 bucks.
You get it right, and you don't have to come to class the rest of the semester. Okay, so let's just say we have a function. I'll give you one, because I give you. See, there's all sorts of functions that you haven't even seen yet. That's pre-cal. You'll do trig functions. Let's just take like x squared, which hopefully everyone kind of knows what that looks like. Okay. All right, then let's take another function like I'll do x. Keep it simple. Which is the line. Goes like this. Okay. You see this region right here between the two?
Yes.
Okay. I'd like for you to take that region here's the number 7. I'd like for you to take that region. I'd like for you to wrap it around that 7, this line, three-dimensionally. Wrap it around it. And tell me what the volume of that is.
Yeah, let's go back to physical.
Let's
Okay.
go back to
Factoring, right?
Or,
back to factoring.
you know what I'm saying? Did you see visually what I'm telling you to do?
Yeah.
Okay. And then find the surface area.
That's too low.
Oh my gosh.
I like that.
I know what you're asking.
Yeah, sure.
You know what I'm asking?
I don't know like a formula to do that.
That's right. And so there's a lot that's involved in that. There's a lot that's involved. That's the best I can do because it's geometric and you can kind of see it, you know?
So typically for a calculator, how long would that take?
That problem, that should take like 5 minutes.
Lovely.
Yeah, it's like,
Yeah.
kind of confusing for me just thinking about like.
All right, we got to keep going. These are good conversations. We'll continue to have them. But we've got to keep moving along here.
Back to work.
Back to work. All right, something like 78. One minus x over x plus 1 over 2 minus x minus 1 over x. Now we have a complex fraction. Fraction over a fraction on top, right? Within some expression that's in a fraction that's in a, this is a complex fraction. So, any ideas here? So kind of like do what we did in the last one, work with the top, clean it up, get a common denominator, then work with the bottom, get a common denominator, then we'll do the whole flipping thing. Okay. So let's see if I can do this a little faster. Since this is a 1, I'm just going to put x plus 1 over x plus 1. And then over here on the bottom one, this is a 2 over 1, isn't it? So I'm just going to put x here and x there. So it'll be a 2x on top on this one. But all right, let's put them together. X plus 1 over x plus 1 minus x over x plus 1. And then 2x over x minus 1 over x. Just x. But it was a 2, so I wrote it as a 2 over 1 so that I could create a fraction out of it. X on top and bottom. Combine on top. Oh, hey, that's good. What happens there? X plus 1 minus x. X's are gone. Just 1 on top. Over the common. On the bottom.
Just x minus 1 over x.
Careful. 2x minus x plus 1, right? Because you're doing minus minus. So be careful with that one. X plus 1 over x. And flip. So we're going to flip here. 1 over x plus 1 times x over x plus 1. Too bad it wasn't the other way around, huh? Because then it would have canceled, but it didn't. So, oh well.
So it'll just be x over x plus 1
Squared. Since we have 2 factors of x plus 1, we can, I'm just making sure my camera's still recording. All right, I think that's going to wrap it up for R7. So let's discuss R8. R8 is nth roots and rational exponents. Everyone knows what their homework assignment is, right? Off the count, except for Stephen. Oh, did I not pass this around? Yeah, I'm going to pass the sign-in sheet, so this will be more accurate of like who's still here. So please just initial next to your name and pass it around. Nth roots and then rational exponents. Rational exponents. R7 was rational expressions, right?
Right.
And that was expressions involving ratios. This is nth roots, so like square roots, cube roots, fourth roots, fifth roots, sixth roots, whatever. And then how that's connected to exponents. Exponents are powers, right? That are fractions, rational. So let's take a look here at what we've got. How about, as an example, number 46. Simplify the following expression: 3x times the square root of 9y plus 4 times the square root of 25y. The purpose of this question is to make sure we're all clear on when we can and cannot combine things together that involve roots. What type of root do you see appearing here? Is it a cube root?
Square root.
It's a square root. How do you know it's a square root?
Because we have to assume it.
You're assuming that the root is 2, right? So if we write that, what we really mean is that there's a little 2 out there, right?
Right.
If it's something other than square root, we have to indicate it with a number. All right, so these are the same roots, square root, square root. If you have 2 roots, you can add them together or you can subtract them as long as they are like radicals or like roots, which means what's underneath them must be the same. The same. You have to have what's underneath them be the same for you to be able to put them together with addition or subtraction. So can you do anything to these to make them look the same? Because right now it's 9y and the other one is 25y. Those aren't the same, so we can't combine them.
You can get the square root of 9.
Okay, so you can actually take the square root of 9, and that's 3, and you can pop that out as a 3. And when it comes out, what does it do over here? It multiplies. Okay, so it becomes 3 times x times 3, which is going to be
9x.
9x. What's still underneath the square root? Because I want to know.
Why?
I know. We got to find any, even if it's bad humor, we have to find it and use it. Okay, plus 4 times, and then again, 25, we can pop a 5 out of this, multiply 4 and 5, 20. So 20 root y. So we can combine these two together because they're the same root. However, the way you do it is you put the 9x together with the 20, and you add them. And the thing is, we can't put 9x and 20 together. Right? What's 9x plus 20? 9x plus 20. So the best you can do at this point is you could do 9x plus 20 in parentheses root y. But someone else might look at that and say, well, all you did was factored out root y. Yeah, right? I mean, that's, someone could say that's what I really did. Yeah, I did.
What do you want us to do?
It's the same thing, isn't it? Combining these two coefficients kind of together and putting them in parentheses is equivalent to really just factoring out the root y. Any questions on that? This would be simplified. That's it. There's nothing more we can do. Now, what if this had been 20x, just for the sake of... Then you could have put 29x root y. Then you could have put them together into one piece. But these both would have had to be, these two would have had to have been the same, like terms. All right. Oh, yes. Let's look at this. Simplify. What number was that? Number 49. Simplify. One over the square root of 2. Oh, hold on. It's actually, they say, rationalize. Can anyone finish this for me? What they're going to want us to do? Rationalize the denominator. Y'all heard that before? I know some of you have, obviously. What do they mean when they say rationalize the denominator?
Don't you multiply their denominator by so like you would multiply it by square root 2?
Root 2 on top and bottom, right? The whole idea is that this expression has a square root in the denominator, doesn't it?
Right.
And we don't want square roots in denominators. Why?
It's confusing.
It's hard to do. They're not easy.
Let's be honest, because somebody told you not to leave them in there, right? Because you've been told not to leave radicals in the denominator, haven't you?
Is there a specific reason?
We're going to talk about that. So, the proper procedure for this is to multiply the top and bottom by 1, right? Which is root 2 over 2. So we just look at the radical that's here, and we just put another one here, and we top and bottom. There's nothing wrong with that, right? That's a 1. It should, so this answer should be the same, shouldn't it?
Yes.
And when you do the multiplication on top, 1 times root 2 is root 2. And on the bottom, what's root 2 times root 2? Just 2?
Yeah, it's 2.
Right? Because it's really root 4 now, right?
Right.
And root 4 is 2?
Plus, you're just squaring the square.
Or you're squaring or square. So there's so many different ways to look at this. You can look at it that way, or you could look at it this way.
Yes,
Right.
that's the way I was talking.
It's all the same, right?
Which then gets rid of
No matter what path you take, as long as you're getting
That's
the
right. Different paths. We're all getting the same place. But the question becomes, why? And that's a question I had. I don't know if I had the question, but then when I figured out later on,
We'll ask you for why several times in the book. That's what you know.
does it? It asks there?
No, in the book, in general.
Oh, yeah.
It asks for why several.
Yeah, this one, though, is something that's just fed to you, and you just don't never question it. They just tell you rationalize the denominator, right? So should we? I'm going to talk about it for you, because I think it's an interesting story. So you know that there was a day, like there used to not be cell phones, right?
Right.
Okay. And you know that I talk to people about that. I talked to my 6-year-old daughter about that. She has no concept that there used to be phones with cords on them, you know? All right, so there used to not be calculators. So if you were taking math back in the 1950s or 1960s, and you were asked to figure out what 1 divided by the square root of 2 is, which comes up quite a bit, comes up in pre-cal a lot, how would you actually compute it? 1 divided by the square root of 2. I don't know. So there were certain numbers that you would have to have memorized. All right? And the numbers that you would memorize were things, the important ones, like pi. You'd remember pi, you know, as many digits as you could. You know, 3.141, la la la. It keeps going on forever, never stops. Doesn't have a pattern to it.
Supposedly.
Does not, right? It's called an irrational number.
Yes.
And there are other numbers out there. Square root of 2 is also an irrational number. It's 1.414. It never stops. There's no pattern to it. It's also an irrational number. That was one of the ones that you would have memorized back in the old days before calculators. And it used to be almost like this kind of show-off thing. Like the level of your math dorkiness was like directly related to how many digits you could go out. You know, and they used to have like contests and stuff like, you know, I know pi out 120 digits, and you know, how about you? And yeah, let me hear it. All right, 3.14, and then they would have competitions. In fact, one of my colleagues knows pi out, at some point knew it out 120 digits. He was able to recite it 60 digits with last couple of years ago, about 2 or 3 years ago. So, I mean, but he's old school. And I know 3.1415. That's about all I know, and that's about all I care to know. Who cares? I have a calculator. If I need to go a million digits, I can just go to Google and do it. You know what I'm saying? Like, so it doesn't matter. So we're back here. We're being told we need to do this, right? We're not being told why we need to do it. We're just being told we need to. So let's go back to the old days, no calculator. Let's try and do 1 divided by the square root of 2. So do you remember how to do division before calculators? Remember this symbol? Okay. So if I'm doing 1 divided by root 2, I would put the 1 inside this box, right? And out here would be the root 2, which I would have memorized 1.414, and I'd have to stop at some point, right, because I can't go forever. And then I have to sit here and think, all right, well, how many times does 1.414 go into 1? And it doesn't, right? It's too big. So we did this thing where we have a decimal, and then we put a 0 here, and then say, how many times does 1.414 go into 10? And you would say, I don't know, you kind of mess with it, and I don't know, maybe you do some arithmetic on the side here. You get your wait, there's no calculators. And so you go, and you finally figure out 7 is the one that works. And then you start going through, and it's just the next one's hard to get, and it's a pain in the ass. Okay? It's a pain in the ass. But if I rationalize it,
Makes it easier.
then what goes in the division box?
The
1.414, and what goes on the outside? The 2. Now, this is much easier. 2 doesn't go into 1, but it goes into 14 7 times, and then I can start working through this very quickly, and it's 0.707, blah, 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 blah. Much easier to do by hand, and so that's the way I'm going to do it.
That makes sense.
And that's why you'd want to rationalize a denominator. It's kind of obsolete at this point. With calculator, it's obsolete. Now, this is not to discredit the method. It's important to know how to rationalize something. It's important to know that. Hey, John, I'm just going to ask you because, you know, you've got something. Oh, it's your phone. I was hoping you were doing something else on that little tablet, so.
Oh, yeah, I just have math on.
I'm sorry?
I have my old math class out. That's all I have.
You have your old what?
No, nothing.
Okay. So, what should I do to John for being on his phone? Should I really take 10 points off his next test?
We'll give him a warning.
Should I warn him? You know the rule, right? We talked about it last class. All right. I'm very serious about it. All right. So, should I give you a shot at redemption?
Sure.
Okay. So why would we prefer this over this?
Because it takes longer to do it the other way. To do 1 over the square root.
Okay. So that's messy. Okay. So at least there you are somewhat paying attention. All right. So we'll give it a warning. That's it, though. That's the one warning for everyone. You don't each get a warning. Oh, man.
Yeah, we thought that was your warning for the year.
No. I just find it disrespectful, you know. Sorry, I'm old school, but I know technology is very hard to separate yourself from this, you know. This becomes you at some point. I think these days it's becoming what people are, but not here. All right? Okay. All right, now let's do a slight variation. It is, but I've got to change it because this is a homework problem. Oh, I'll do the homework problem. How about that? I'll do it for you. But I won't tell you which one it is. I won't tell you what number it is in the book, so you'll have to go find it yourself. But if you do your homework, you'll run across this. What's the difference between this one and the previous one?
It has completely different numbers.
Okay, so all right, come on now. Come on now.
Well, for one, you've got 3 times the square root of 5 on the bottom.
Okay, so you've got not just a root, but it's 3 times the root and plus 2. So you actually have 2 terms in the denominator, don't you?
Yes.
2 terms. Here you only had 1, and when we have 1 in the and it's a radical, we just do root 2, and that's pretty easy to take care of, right? Pretty easy to take care of. But we saw there wasn't much value in it, like big picture, there wasn't any, much value. But when we have 2 terms, it's not as simple as just root 5. Why not? Don't write this down, but why would this not help?
Because you still have the whole thing.
Yeah, because when you do the multiplication here, right, you're going to get 2 root 5. And now when you do the multiplication here, yes, the root 5 and root 5 will become a 5, but you still have a root down here, and the whole point was to not have a root down there. So that doesn't save you to just put a root 5. So instead of coming in with root 5, anyone know what we come in with?
2 plus 3.
Close?
That's what.
Close.
3 root 5?
2 minus 3 root 5. So what we do is we look at the denominator, and we come in, and we say, all right, I'm going to multiply the top and bottom by this.
So how did we get that?
Yeah, I don't know. Abby, you said that, right?
Yeah.
Okay, so can you tell everyone why you did that? Yeah, so you remember seeing this at some point? Yeah. So why do we do it? You're about to see why it works. First, let's talk about what it's called. This is called the conjugate. Okay, so you look at this right here. It's 2 terms. The conjugate of it is itself with whatever signs here switched. So if this is plus, that's minus, that's called the conjugate. If this was minus, you do plus here. Okay, so you just switch the sign between them. Conjugate. When you multiply the conjugate, something good is going to happen. And I'll illustrate it over here. Let's say I gave you this. What is its conjugate? A minus B? What is that? You recognize that? That's a difference of squares, isn't it? So anytime I do this and I multiply, I'm going to get a squared minus b squared, aren't I? So when you have something and you multiply it by the conjugate, what happens in the end is that whatever the a is, whatever the b is, you square them and you subtract. So if I'm looking at this and I come in with this conjugate, my answer is just going to be that squared minus that squared. And when you square both of those, there's not going to be any more root. Now I'm going to do the actual multiplication, but I'm trying to show you why. Someone said, why do we do it? Like, why do you come in with that? It's because you're creating a difference of squares. You're forcing it to happen. What do you need to? Does the sign-in sheet get around to everyone? Everyone's got the sign-in sheet. All right, 4. I'm gonna do this right here. So 2 times 2 is 4. What's 2 times negative 3 root 5? So what's 2 times? Yeah, you multiply the 2 and the negative 3, you get negative 6. So negative 6 root 5. That root 5 is trapped, right? You can't mess with that root 5? All right, so what's the next piece on the top?
Root 5 times negative root 5.
Which would be?
Negative 2.
Negative 2 root 5. Why do we like to put why do we like to put the 2 out in front of the root 5? Like, why not write root 5 times 2? You might think that's 5 times 2 and 10, and you might put it underneath the root. You don't know for sure. Sometimes people get kind of lazy with these bars, and someone would think, oh, later on, wait a minute, that was a 10. Or, so it's just good convention to put the number outside in front so you don't mess it up. That's the only reason, though. Next, here to here, plus 3, and then root 5 and root 5 together is 5. So I could have multiplied that and put a 15, but I'm going to do it on the next step. So this piece right here was the root 5 times the root 5. That's the top. The bottom, 4 minus 6 root 5 plus 6 root 5 minus 3 times 5 again. So I did that one quicker. 4, negative 6 root 5, positive 6 root 5, positive 3 and negative 3, negative, oops. What's that supposed to be? 9. Sorry about that. Glad I double checked that. Positive 3, negative 3 is negative 9, and then root 5 and root 5 is 5. So is in terms of a number, what number do we have on top?
4 minus 8 root 5.
4 minus 8 root 5, and then plus 15, right? How about we put the 15 and 4 together? So 19
19 minus 8 root 5.
minus 8 root 5. And then over, these middle ones are gone, aren't they? Which is why we did it, right? It's going to guarantee not have roots in the bottom. 4 in the front, take away 45 in the back. Negative 41. It's rationalized. You have no root left in the denominator. Now, you could argue, yes, again, you could say, hey, look, what's the point of this? You have a calculator, right? But when we look at something like the next problem and last problem of the day, which I probably won't, bless you, which probably won't finish, I'll just get you started on it. This is one of your homework problems. This is number 62. I'll tell you which one it is. It wants you to find or rationalize the denominator. This is looking a lot like calculus right here, like calculus, something you would come up with in or see in calculus. So I don't want you to take what I told you about the calculator thing and just be like, anytime they say rationalize, they're stupid. Yes, if you're trying to compute a number, a numerical value, you don't need to rationalize anything because you can just use a calculator. But in terms of an algebraic expression like this, we will need in calculus to rationalize the denominator, and you can't get around it. So you still need to know what to do. The technique of rationalizing something is important. So what shall we do here?
Multiply the top and bottom
By the conjugate of the denominator, which would be?
Root x plus h plus root x minus h.
Do the same thing up here. Same. And multiply that out. And just be careful. And that would be the answer. You'll get to the answer. And I'm going to stop there because I don't have enough time to do it. I don't have enough time to ask you to do it. And it's one of your homework problems. But that at least tells you what you should do. All right, so do as much as you can of the homework. There's a lot there. Make sure that you do leave your assessment. Everyone graded their own assessment, right? Okay. And just leave it up here. I'm going to back this table up. That way people. Yeah, if you want to, I would prefer it be stapled. I think I asked for it to be stapled, right? Let me see. Do all work on separate paper. No, I didn't say staple it, but so you don't have to.
So would that just be 2x?
Where's that? 2x, the whole thing?
Yeah.
I don't know. I'm not going to say yes. I don't even want to look at it. I don't even want to. I want you to figure out what it is. Have a good weekend, everyone. Just drop them right here. Oh, I don't need that piece. Just the assessment. Just your work is all I want, with your name on it and your grade.
Sorry, I apologize. I didn't mean any disrespect by that.
Okay. Well, as long as we're clear. I
Yeah.
mean, I didn't want to penalize you, but at the same time, I don't want to